Okay, thanks for making it to the second part of these lectures. I don't know how much of this you remember, but the last time where I stopped was with introducing the notion of generalized non-contextuality as the ontological identity of operational indiscernibles. And I defined two things there. One was preparation non-contextuality, so P here is for preparations. And the other thing was measurement non-contextuality. And preparation non-contextuality was the idea that if two preparation procedures lead to the same statistics, they're statistically indistinguishable, regardless of whatever measurements you throw at them, then they must be represented by the same distribution over context states in your ontological model. So the mu p for them should be the same. And measurement non-contextuality was a similar notion, except that now you look at effects which are operationally equivalent, like measurement events, which are you cannot distinguish regardless of what preparation you measure them on. And so if you see the statistical equivalence at the operational level, a natural explanation for that is that ontologically they're the same thing, that the response function, the psi, the map psi, is the same for the two effects, right? So that was this idea. So today we're going to look at how to use these definitions that I have that I introduced to, in some sense, rescue the central insight of the quotient spectral theorem when you are in an operational context, when you don't assume quantum theory or relative measurement. Okay, so before that, I need to formally introduce what I mean. I used this word last time, but I didn't really introduce it, but I guess I said what it was. So these are properties of an ontological model, right? Like ontological model. I'll only prepare and measure experiments, so I'll only talk about preparation and measurement non-contextuality. And so I define two properties of such a model: preparation non-contextual, measurement non-contextual. I'm going to add one more property that will allow us to think of the quotient spectral theorem in this framework. And that property is outcome determinism. So if you remember, for the measurements, for any event, measurement event, we had associated some response function, which given some lambda will assign some probability to the outcome k for the measurement m. And we didn't say anything about this response function except to say that this gives you some probability for this outcome given the measurement setting and lambda. Right? But we want to impose a restriction now on this. We want to say that in fact we don't want to allow like arbitrary probabilities for this, but we're going to insist that that given your knowledge of lambda, you know exactly which outcome is going to happen with this measurement. Okay, so lambda in some sense contains complete information about the measurement outcome. So that these probabilities are deterministic, they're 0 or 1. Okay. So outcome deterministic in the sense that given lambda, your outcome is determined, okay, by lambda, and of course the specification of the measurement is so that's what I will mean when I say outcome determinism. And this is true for all effects in the theory. Okay? So for all outcomes of a given measurement and for all measurements in the operational theory. Okay, so once I define this, then just from the definitions, you should be able to see that quotient spectral non-contextuality. So this is my shorthand for quotient spectral non-contextuality. It's a conjunction of two assumptions that's equivalent to measurement non-contextuality. namely asking that this response function should be the same for operationally equivalent effects, and so logical and outcome determinism, namely that this response function should furthermore be deterministic, right? So if you recall the figure from the last time in any sort of hypergraph where you have this kind of sharing vertices, you can begin to talk about measurement contextuality, right? So just draw that little piece of the big thing that I drew last time. So if you were thinking of these two measurements, and if you now you're not imagining that they're necessarily coming from quantum theory, but they could be from some operational theory. And so in the operational theory, there will be some labels for these measurement units. So for example, for measurement 1, this is outcome 1, outcome 2 for measurement 1, this is outcome 3 for measurement 1, and this is outcome 4 for measurement 1. Okay? Now, for measurement 2, this one is the outcome 1, so outcome 1 for measurement 2. This is outcome 2 for measurement 2. This is 3 for measurement 2. And this one is 4 for measurement 2. Okay? So these are your measurement events here, for example. And the reason I've identified so the very fact that it's represented by one vertex, these two measurement events from different measurement settings, is basically stating operationally, it's a graphical way of representing the fact that the outcome 4 of measurement M1 is operationally equivalent to the outcome 1 of measurement M2. Okay? Like the fact that no matter what preparation I use, I will get the same statistics for these two outcomes, which come from different measurement settings. So they're operationally equivalent. So this implies by measurement non-contextuality, right, that the response functions I should choose for them, so 4 given M1 lambda should be identical to the response function to the other one. So this is of course an assumption, it's not a logical implication, it's only true if you assume measurement non-contextuality. And yeah. So this was that. And when I say outcome determinism, I'm adding the further restriction that these are 0, 1 value. And so now you can go back to that coloring picture, right, where we're talking about assigning 1s and 0s and looking for this map, the map C assigning values 0s and 1s. That's effectively in this framework the assumption of measurement non-contextuality and outcome determinism. Okay? So the existence of that map C basically translates to the existence of a measurement non-contextual and outcome deterministic ontological model. Okay? Is that okay? And one thing maybe I didn't say last time was the reasonableness of this assumption of non-contextuality. It sort of hinges on, it's basically like intuitively you're trying to say, you know, there's no experiment in my theory that will distinguish these two experimental procedures. So what does that tell me about these procedures? It tells me that whatever else is going on, it's reasonable to assume that in the underlying ontology of this experiment that these two procedures are represented the same way. And the reason we want to say that is it's kind of a parsimony kind of principle, right? Like the idea that we don't want to add extra degrees of freedom in your ontological description that don't make a difference in an experiment, right? So that's kind of the motivation, because and mathematically that means that if this is true, then this follows, right? Like this implication is obviously true just from the definition of an ontological model, right? Because when we say that probability of k given m p is given by mu lambda, so k given m lambda, then two effects k given m and k prime given m prime will obviously be operationally equivalent if the response functions are identified, right? That will be true for all possible whatever distribution we want to average them with respect to it, right? So this direction is obvious. So this is a sense in which non-contextuality is an explanation for the observed equivalences.
So am I correct in thinking that if we have, say we have an ontology, right, that's potentially very expensive, we can make it a measurement non-contextual by associating different ontological entities, and so we can always, in some sense, always arrive towards a measurement non-contextual ontology by taking a quotient in some sense.
Yeah, exactly. So it's a notion of kind of, you want to quotient away things that are not making a difference to the experimental statistics, right? The question is, can you always do this, right? And what we will find is that you can rule out the existence of such models for quantum theory, for example. Like, so we want to find conditions on the operation of statistics under what kinds of observed statistics. Is it impossible to imagine that there is such a model, which is measured non-contextual? Okay, so it's a no-go theorem. The nature of a no-go theorem is you motivate an assumption, you motivate why it's a natural classical assumption of classicality. So I was trying to motivate that, like the fact that no experiment in your theory can distinguish that, which means that even if there's a deeper description, you want to assume that that deeper description doesn't carry any redundant information, like it sort of doesn't. Yeah, basically, otherwise, if this fails, you're basically saying that in the ontology, there are these degrees of freedom that you will never see. You will never have access to them in an experiment, right? It's a bit like in Bohmian mechanics, that you have some supercritical causal influences, but you never see them effectively, and things get washed out. You have no signal at the operational level. So it's a sort of fine tuning, right? Like if this thing fails, what that means is that these things can be different in the ontology. For some lambdas, they can be different, but these differences are fine-tuned away when you coarse grain. When you coarse grain, the equivalences are restored, right? So in a contextual model.
In other words, you can always, like, given an ontology, you can always find a kind of measurement non-contextual that you can, like, in principle, you can always quotient, but then the problem becomes with the outcome determinism. Is that correct?
Yeah. So given the quotient spectral theorem, that's what we realized, right? Like, so this is where I was going to get to basically. So as I said, existence of this map C. So the quotient spectrum is the non-existence of this, right? Like of C is equivalent to existence of measurement non-contextual deterministic ontological model for your statistics, for your operational theory. And so that means that, and remember, this was this had the flavor of logical contradiction, right? It was impossible to assign these values. So which means that these two assumptions lead to a logical contradiction, right? Measurement non-contextual and outcome determinism. And if you want to relieve that logical contradiction, you can give up either one of them, right? I can say that okay, since KS theorem is true, and that is basically saying there doesn't exist a C that mapping, which means that these two assumptions fail, right? Like the conjunction of these two things fails. Right, so this is just a knot right on the end of this thing. And so that means that, at least in terms of these two assumptions, at least measurement non-contextuality fails, or it's the case that outcome determinism fails. Right? Like one of the, you can give up one of them. And then you don't have a contradiction if you give up one of them, right? So the strategy that when people usually say contextuality in the sense of the quotient spectral theorem, they want to insist on outcome determinism, so they want to hold on to outcome determinism, but they want to give up on measurement non-contextuality, right? So traditionally, contextuality, I'll just say quotient spectral contextuality just to distinguish it from the generalized one, is basically saying it's not how I'm going to interpret the word. For me, quotient spectral contextuality is the failure of this joint assumption But in the literature, when people say contextuality, they really mean the failure of measurement on contextuality while retaining outcome determinism. Okay? Which was this idea that if I'm assigning values, they should be assigned in a contextual way. Right? So in this contradiction, for example, I was trying to avoid drawing the whole thing, but I think I have to draw it again, and I enjoy drawing it again. Just to make it manifest that what I mean by the failure of measurement on contextuality while retaining outcome determinism here. Right. Okay, so if I complete this figure, so this is your 3 and 4. This is 5, and this is 6. And then there were 3 more measurements. I will erase these for now. 3 more measurements come out of these 18 vectors, which are basically this one. Oh, sorry. This one. And final one is this one. Right. So last time I just argued that since every vector appears in 2 bases, when you write down the set of 9 equations, that you have on the left hand side 2 times some integer, so that should be an even number. On the right hand side you have 9, which is an odd number, so therefore you cannot color them 1s and 0s. Right? That's what I said. But what if you did want to color them, right? Like what strategy could you adopt? Like you can assign them dimension on contextual and you can color them. Right? So for example, if I start with a 1 here, then these have to be 0s. 0, 0, 0. And then let's say I put a 1 here, so these have to be 0. And these have to be 0. And maybe I put another 1 here, so this has to be 0. These have to be 0. And so that forces me, because there's a 0 here, a 0 here, and a 0 here, that forces me to put a 1 here, right? If I think of this measurement. If I think of this event as part of this measurement. Okay, and then, so that means that I should put a 0 here, right? But if I put a 0 here, then this is thinking of this event as part of this measurement, right? However, if I thought that this event was coming from this measurement, then I should be putting a 1 here, right? So one way to avoid the contradiction is to just give up on measurement on contextuality, while holding on to outcome determinism is the fact that I'm assigning 0s and 1s here. And if I want to hold on to it, I have to allow for measurement contextuality. I have to allow for contextual assignments of values which are sensitive to which basis you're measuring it, for example, right? Which means that your ontological model has to carry information about the measurement basis, which your lambda has to know which basis you're going to measure things in order to predict what's going to happen, right? So which is kind of like, why should the state of the system care about what you're going to measure later, right? Like, so that's why it's unnatural to kind of assume this kind of contextuality. And that's also the sense in which one says that unperformed measurements have no outcomes, in the sense that, at least you cannot assign outcomes without knowing which measurement someone's going to do, right? So they do not have an intrinsic property called the measurement outcome, right? Like, if you want to declare such a property, you have to take into account all possible measurements someone could do. For each one you have to say what's going to happen, right? So that's how it's usually seen. However, there's obviously another way out of the contradiction, right? And which is what the criticism here is about, which is that it could also be that so this is one possibility, but the other possibility is that you hold on to measurement on contextuality, and the thing that fails is outcome determinism, right? What does this mean? this is relaxing the other assumption that I'm assigning ones and zeros. Now, if I have a probability valued assignment, if instead of the function c, I was looking for assignments of probabilities to these vectors, to these points, vertices, then there is no straightforward contradiction, right? Because the things don't have to add up to an integer on the left-hand side, 2 times an integer. There could be a fraction or something. Or like I mean, the sum of the probabilities of assigning these 18 things could be a fraction that when multiplied by 2 gives you an integer which is 9, right? Like, so it's not ruled out a priori. And of course, if you look for the set of all possible solutions to that system of equations in probability valued solutions, then that set is not empty, okay? And I can just give you a simple example of such a solution, just so without actually exhaustively enumerating the solution set. So the first thing that I tried to point out was how the usually lesson of the quotient spectral theorem is taken to be this, but an alternative lesson could also be this, and then you don't have a sort of no-go theorem for non-contextuality, strictly speaking. Then you just have a sort of a no-go for determinism somehow, which is I will come to that. So here, for example, this is a possible solution. Halves here, 0 here, 0 here, 0, 0, 0, 0. There's a 1 here, 0, 0. And maybe I'll make it symmetric. This is 1 here, and so 0, 0. And what else? Yeah, and then I can just add a 1 here. So that's 0, 0. Yeah? That's a legit solution, I think.
Is there an easy way to transform like solutions that violate measurement on contextuality and take that and transform it to a solution that violates outcome determinism and back? Like, can I
so basically
between the types of solutions?
So in the case of when you assume measurement on contextual outcome determinism, we know that there are no solutions, right? Like that was the logic.
But if you relax one of them, you can find solutions.
Yes.
Can you? But then the solutions you find relaxing one don't satisfy the other one. But is there a kind of a function or something that I can say, okay, I've given one of these solutions, can I transform it into a different solution?
Yeah. So so the mathematical question you're asking is that if instead of looking at these, I was thinking of these 18 variables. If instead of these 18 variables, I replace them with 36 variables, basically 2 copies of each, where I label them by the context in which they appear, then there are deterministic solutions for that thing, because the contextual assignment here was a deterministic solution of that type, right? And you're asking if from there you can go to these kinds of solutions, and that's true because this will be like a convex mixture. It'll be like a half probability where this is assigned. You can express that as sort of so in that deterministic kind of space where every variable has 2 copies, you have these 0, 1 valued solutions. They're possible. However, there'll be like a subset, like a strictly lower dimensional subset of it, where mixtures of these things will give you solutions of this type. Is what I'm trying to say.
Right, and does it work the other way? Like, can I just replace the 1/2s with 0s or 1s and have an outcome that is deterministic with non-measurement contextual solution?
No, because I mean it depends on what you mean by the question. Because what I'm trying to say here is that the very act of identifying measurement events and saying that there's one variable that assigns probabilities to both of these instances of measurement events, like for example this vertex, is an assumption of measurement on contextuality. So when I write down the equations, 9 equations, that is an assumption of measurement on contextuality. Now to get to say that I want to rescue it, so the trivial way to rescue it is to make 2 copies of every variable and say that, okay, that somehow I rescued it. But have you really rescued it? You haven't, because conceptually, at an operational level, if you look at the statistics, even though you make two copies, in your ontological model you're going to represent them differently, those two copies statistically still give you the same statistics, like on the quantum level, right? So even though it may look like just because I labeled everything things are non-contextual, they're not really, because they're still operationally equivalent, right? They're still, so yeah, so I don't know, does that but is this clear at least, like the fact that the first instance was this contextual assignments, where you basically can make two copies of variables and do that, determinism is possible then. But the other possibility is where you refuse to make two copies of the variable because operationally you see the same statistics, so you refuse to make two copies because you're like, okay, they're really the same. I want to insist on that because there's no experiment I can do to distinguish them. But I'm willing to give up outcome determinism, right? And like, why should nature be fundamentally deterministic? Why should I assume such a thing, right? Like you can make that statement. And so you're willing to give up on any sort of determinism given these object states. And then you don't have a contradiction, in fact, you have solutions of this type. That's my limited point right now. So, but what does this mean? What this means is that now you have to compare the situation. So what's happening with the Contextuality theorem with Bell, right? So Bell's theorem it formally says that there does not exist a locally causal hidden variable model of quantum theory, or just for no signal. If you violate a Bell inequality, such a model doesn't exist, right? It's for any no signal theory. And when the definition of local causality doesn't require you to assume outcome determinism, it doesn't require you to assume that you're assigning outcomes deterministically. Okay? In fact, you can relax that assumption and Bell's theorem still goes through. So in Bell's theorem, I do not need to say that so basically the operational statistics, okay, the formal statement is that at the operational level, operational statistics, after coarse graining and everything, statistics from a locally causal invariable model. So the set of probabilities you get is identical to the operational statistics from what's called a locally deterministic, which is the original type of model that I have in mind, hidden variable model. Okay, so the difference between these two is that in a locally deterministic model, every given the hidden variable lambda, which is sent to multiple parties, the lambda fixes a function from the input setting of the party to the output setting. So it determines which outcome is going to happen given the input setting. That's outcome determinism. Okay? If you say it's a locally deterministic model. If you say it's a locally causal model, then all lambda has to do is to give some stochastic map from the input setting to the output. Okay? It doesn't have to say which output occurred. It just has to give you a stochastic map. Right? The claim is that these two situations are empirically equivalent. That when you go to the operational statistics, the correlations between outputs given inputs in a Bell experiment, that statistics is insensitive to which of the two options you choose for modeling your experiment. So Bell's theorem doesn't require outcome determinism as a fundamental assumption of the theorem. Okay? All it needs is local causality, which is motivated by the fact that the parties are space-like separated. Therefore, my outcome cannot be conditioned on the settings of the other parties. It can only be conditioned on this variable in the global past, which is lambda, right? And my local setting. So it's local causality in that sense, but not on remote settings, right? And that doesn't require any claim about probabilities. Like it doesn't require a claim about determinism, right? Now, so these are two ways you can think of Bell's theorem. And so, of course, like, since you don't need to assume determinism, you can kind of say in some sense that Bell is a more robust no-go theorem than Contextuality, because in Contextuality, when you give up determinism, outcome determinism, the contradiction disappears. This is what we're showing here, right?
Yeah, but isn't it the same with Bell? Because you can't can either give up like locality or so the locality condition is what I do here doesn't change what's going on there, but isn't it also assuming that the values are already predetermined before?
Maybe I'll try to write it out. So what the mathematical distinction is. So it's this in a two-party Lattice experiment where A and B are the local outputs and X and Y are the inputs. A locally causal model is one where you have some distribution over lambda. So this is your invariable, which is sent to the different parties, and then conditioned on this for the first party, there's some distribution for what outcome this party will see given lambda and some setting, and there's a distribution for the second party B given y lambda, right? So this is local causality. Just putting that up, I wrote. Now this doesn't require that these things are valued in 0, 1. Okay? Although I can always do that. The reason I can do that is because of the particular structure of local causality, because it factorizes, like the distribution factorizes, it's kind of correlated in some way, but it also factorizes. Given lambda, it factorizes, right? So that factorizability is key, basically, to the fact that you can relax determinism as an assumption, okay? So I can think of this, I can completely de-randomize these measurements, right? Like, imagine that these are stochastic maps, right? Like, from these variables to this variable, these variables to this variable. Now all I need to do is just absorb all the randomness of these guys into this distribution, right? I can always do that. Like, I can think of this as sum over some further specification of some local things, like some hypothetical numerical, let's say lambda, which is local to the party A, and given this lambda prime, this A is completely determined, let's say, is of some function of x lambda prime, and there's some distribution over lambda prime given lambda or something like that, right? So you're basically de-randomizing this thing by thinking of it as a convex hull of deterministic assignments, right? Any stochastic map can be thought of as a convex mixture of deterministic ones. That's what I'm trying to say here, right? So, and then you just move these things here. You just absorb them in this, right? And then what you will have eventually is this thing, right? Like you will have some new variable, I'll just call this some omega maybe, okay, which absorbs all the randomness from the local measurements into the source, the original lambda, and it says that there's some distribution of over this omega, and then there are deterministic maps given omega, because omega contains all the local information that was fixing the outcomes locally, right? Like, and so given so x and omega, it fixes this thing, b, and maybe there's some other map here for y and omega, right? So this one is a locally deterministic ontological model. This one is a locally causal ontological model, and I just showed you how to go from locally causal model to a locally deterministic one. And similarly, you can go the other way, because locally deterministic model is by definition locally causal, right? Because it satisfies the factorizability condition. So the thing you get here, this operation statistic, stays the same, regardless of which of the two strategies you adopt. Now, my claim is that in Bell's theorem, because of the special structure of the local causality condition, which has this factorizability property, you can absorb the randomness into the source, right? We don't have any factorizability and stuff in quotient spectra because it's a single system. Like, you're not going to argue that some setting is not affecting this outcome or something like that, because that's an extra assumption you're imposing. It's not coming from some causality constraint or something. Okay? At least it's not coming from relativistic causality. It's not coming because you have space-like separation and things cannot affect each other. So that's the sense. So there's an unsatisfactory feature to the quotient spectra theorem, which is the fact that relaxing determinism just kills the theorem, right? Like there's no more contradiction anymore, so what do we learn, right? And this is also kind of conceptually the reason why you see so many more applications of Bell's theorem and quantum information and device independent stuff than of quotient spectra, because it's very hard to guarantee anything about the quotient spectra theorem, because like at least in its original formulation, it requires all these assumptions, right? And now we're going to go and see how to relieve this problem. Can we still have a contradiction? So this is a way out of the quotient spectra theorem. And I still want to obtain a no-go. I want to obtain a no-go theorem that uses only preparation non-contextuality and mesh non-contextuality. So I give up on determinism, okay, but I invoke an extra assumption, which is the other assumption of non-contextuality, which has to do with preparations. This is not present in the literature on quotient spectra theorem, because this is a new assumption which was motivated on the same grounds as mesh non-contextuality. The grounds being that operationally indistinguishable things should be represented identically in the ontological model, right? So that's the conceptual justification for why this is a reasonable assumption. It's at least as reasonable as mesh non-contextuality, because if you take the motivation for mesh non-contextuality to be the fact that you shouldn't add extra details in your ontological description that do not make a difference to the operation statistics. If you take that as the motivation for the assumption of non-contextuality, then this assumption is equally motivated as this one. Okay? So that's sort of like so what we're going to do, the next thing I'm going to do is use these two assumptions without any outcome determinism, so there will be no outcome determinism assumed anymore, and see how what we learned from the quotient spectra theorem can be ported into a framework for contextuality which doesn't assume determinism. Okay, so that's the next one. So all this was just building up to like trying to get motivation for why I'm going to show you the thing I'm going to show you next. Okay, the problem that it solves. The problem it solves is proving a no-go theorem without assuming determinism. But it uses preparation non-contextuality. I mean, obviously it has to use something, because as we see that there is no contradiction here, right? It's with mesh non-contextuality alone. And I will use the same example so that, like, you can think of this as a working example to sort of understand the underlying concepts. The same ideas apply to any proof. I shouldn't have erased that because I'm going to drive. Sorry. Yeah. Okay, so the question is, this is the question we are answering: how do we rescue? Because the quotient spectra theorem is saying something interesting. It's just that it's not saying it in the most operational way possible. So how do we kind of make it operational, right? How do we rescue the type of non-classicality hinted at by the KS theorem without assuming outcome determinism, just like for Bell, right? Like Bell, it's easy because so there's a thing called Fine's theorem, the thing that the argument I was giving you for local causality and local determinism, the equivalence between them. It's a kind of part of something called Fine's theorem. It's due to Arthur Fine in the 1980s, where he basically gave a rigorous justification for that. Without assuming outcome determinism. In particular, so we want to make it operational, right? Operational. Okay, so that's what we're going to try now. Okay, so the first thing is I draw the thing like rays again. My goal is that by the end of these lectures, you're able to draw these yourself. I draw them enough times. So it's 1, 2, 3, 4, 5, and 6. And then we have 7. And we have 8. And then we have 9. Sorry, it's not drawn very nicely. Okay, that was the original contradiction. And how do we rescue it is the question, in the absence of determinism. I mean, we're obviously not going to rescue the contradiction directly, but what we're going to do is we will see the connection of the contradiction with the operational version once we have the operational version. So everything I say here is in this paper, which is this operationalization. So it will probably give you more justifications and more of a conceptual development than I may have time for here. But I think what I say will capture almost everything in the paper. Okay, so if you remember, like the last time I was saying things about projective measurements and POVMs and stuff like that, right? Like that it's kind of problematic to think of a quotient spectral theorem for POVMs because you can have almost trivial proofs of that, and that's why it's not an interesting notion of classicality for POVMs, right? So the underlying sort of thing I was getting at when I was saying that it's uninteresting for POVMs was because you have these trivial kind of examples. Now, but what's the lesson we draw from the existence of those examples? The lesson that we draw here, I mean, it's not explicitly stated that way here, I guess. I don't know if it is, but is that the projectiveness of a measurement in quantum theory. When I say projectiveness, I'm trying to be a bit vague about, I'm not saying projective, I'm just saying projectiveness. Like one aspect of the projectiveness of a measurement is its of an effect is its predictability. Okay. So when I say predictability, I will mean whether for a given effect in your operational theory, there is a preparation in the theory that will make that effect deterministic, perfectly predictable for that preparation, not for arbitrary preparations, but there exists at least one preparation for which it's perfectly deterministic, like the outcome, right? So, of course, in quantum theory, we know that if you prepare an eigenstate measured on the same basis, you will get that in deterministically, right? So we're abstracting away that idea, right? In operational terms, that's what we want to do. Okay, and that's basically the only property of a projective measurement that we're going to need to be able to state to operationalize things. Okay, so
that's why I said maybe the normal one property.
Yeah. But the thing is that normal property will
again the space will be smaller when it's
the thing is, okay, maybe we come back to it after I have the formulation written down, and then we can have a discussion about that. Because because the thing is that the framework requires this additional ingredient coming from preparation on contextuality, and then that kind of makes it harder for me to say things in terms of measurements alone. I need to also talk about preparations. I mean, of course, the information about preparations is contained in the norm in some sense, but so when you only talk about quantum theory, then yeah, I think you can kind of. So basically, the rule, what eventually happens is that for quantum theory, the kind of response functions you should assign to your POVM or any effect, it should take values in the spectrum of that effect. You can derive it as a consequence of preparation and measurement contextuality. The fact that if your operational theory is quantum theory and you are thinking of POVMs in quantum theory, and you want to talk about a non-contextual model for these, then firstly, you shouldn't be assuming outcome determinism, that you assign 0 1s, you should allow for probabilities. But actually, you shouldn't be allowing arbitrary probabilities, you should be allowing exactly those probabilities which come from the spectrum of your effect. And this can be proved starting from this preparation of measurement contextuality. It's not an ad hoc assumption you're adding, it's something you can derive given the structure of quantum theory and the assumption of preparation and measurement contextuality. So that's something in this paper, Status of Determinism, that I referred to last time. But I will not go into that here. I will try to keep the discussion strictly operational and see if we can learn something, like, without directly going to the quantum formalism. Okay. Of course, it's inspired by the quantum formalism, but it isn't required, like the eventual statement of the results. So, I'll say perfect predictability of a measurement outcome so let's say it's k to the m is the effect we're interested in. I'll call it perfectly predictable if this thing is true, right? Like, it means that there exists some preparation in the theory, call it PIK, belongs to the set of preparation procedures in the theory, such that, call this PK and MI maybe, such that the operational statistics dictates that this probability, like, namely this effect measured on this preparation, is 1, right? That's just take it as a definition. Like, so this is obviously true for if this was k given mi was in quantum theory, for example, if it was just I don't know, just the outcome spin up for a z measurement, and your preparation was basically the same. Then obviously the Born rule clearly tells you that it has to be happen deterministically, right? It's not true for other preparations, but it's true for exactly this one, right? But I just mean that there's at least one, right? Yeah. Okay, so that's that. So keep this idea at the background, like at the back of your mind. It's not going to directly be involved in the derivation. I mean, in some sense, it is involved in the derivation, but let's see. Okay. So there are these 9 settings here, right? Like, so there's 9 measurements. So there's mi from I equals 1 to 9, and there are these operational equivalences, right? Like, every vertex that is shared between 2 hyperedges represents an operational equivalence of 2 measurement events, right? So there are all these equivalences which come from the figure, which is 1 given m1 is operationally equivalent to 4 given m6, for example, right? If I label them disaccordingly, right? 1, 2, 3, 4, 5, 6. I'm calling this the 6th measurement. So the 4th outcome of the 6th measurement is operationally equivalent to the 1st outcome of the 1st measurement, and so on. I can write a whole list of these things, right? Just reading them off from here, right? So the operational content of this hypergraph is these operational equivalences that hold between different measurement procedures in the operational theory, right? Now we're moving away from the picture where we're thinking of these as projectors and this as complete resolutions of the identity. Now these are just some operational events which have which define measurements, right? Like, and so they have these operational equivalences which are captured in the hypergraph. And when we say measurement contextuality, it's the assumption, we already talked about this, that these response functions are identical, right? Okay, I've not added anything new so far. But now we want to add new things. We need to use preparation on contextuality because we don't have determinism anymore. And so I'm going to define preparations. Okay. For each I, so I'm going to call these, let's call them preparation ensembles in some sense. Okay, so these are different each preparation is a preparation of an ensemble of states. Okay, and we take them directly from here basically. Okay, so we take So for example, for index I equals 1, I associate with I equals 1 4 preparations, or let's just for each I, where I is 1 to 9, with each outcome I associate some hypothetical preparations, right? So I1, I2, I3, and I4. Okay. So I want to think for each event here of a corresponding preparation. Okay. I'm not saying what these preparations are, but these are just some abstract preparations in your theory, operational theory. Okay. But they satisfy a certain property. Okay. And the property they satisfy is that if I look at the average preparation that I obtain, so for our purposes, I'll take, in general, you can generalize this beyond the uniformly random case, but let's say it's the uniformly random mixture of these guys. Okay? So, I2, three, yeah. So this statement is just saying that there are 2 preparation procedures I could do in my operational theory. One is that I take, this preparation. I flip not a coin, but like a 4-sided coin or whatever. Yeah. So I generate like a random number between 0 to 3. Okay, with a house 0, 1, 2, 3. Real integer.
You flip a tetrahedron.
Huh?
You flip a tetrahedron.
Yeah, flip a tetrahedron, in an appropriate dimensional space, I guess it should land on one side. Yeah, okay, so in any case, so this, what am I saying? I'm completely distracted by that. Yeah, so it's a mixture, right? This is a procedure which involves preparing this, or this with some probability, okay? So you can think of it as somehow preparing an ensemble, right? Like if you prepare an ensemble of states with some respective probabilities, equal probabilities, it's an ensemble. But when you mix it, you're preparing a new thing, which is the density matrix associated with that ensemble, and using your quantum intuitions. And that density matrix could have been prepared in a different way. It need not have been prepared by mixing these things. It could have been a reduced state of some bigger state, for example, or some pure state, right? So the density matrix by itself doesn't tell you how it was prepared. It could have been prepared in infinitely many possible ways. All of those are different preparation contexts for that density matrix, right? So okay, why did I write Google? Like this is the definition right now. Okay, so here I'm assuming that this preparation is done in this way from the ensemble, and there's an operational equivalence I want to use. So I want to say that PI average is operationally equivalent to PJ average for all I and j. Okay, so for all ij are from 1 to 9. So this is claiming that even though these atomic things might be distinct for the different ensembles, when you average them for each ensemble, you get preparation which is operationally equivalent, like for all of them. Okay, so in quantum theory, this is just the idea that if you take your eigenstates and mix them equally, you get the maximum mixed state, right? And the maximum state is the same for regardless of which basis you prepare it from, right? It's operationally equivalent. So in a quantum implementation, that's how this will be realized, right? So this is where the assumption of preparation non-contextuality is going to come from. So if I assume this, then that means that these guys, mu pi average lambda equal to mu pj average lambda for all ij and for all alpha distribution, and I just define this to be something that's independent of I, some distribution over lambda, some neighborhood lambda. Okay. So this is a consequence of preparation non-contextuality. This is not true in arbitrary ontological models. It's only true in a preparation non-contextual ontological model. Okay. And that's what we want to use. We want to use this and this in order to see what we learn from this quotient spectrum inspired setup. Okay? Okay, so to see what we learn from this setup, we're going to use a particular operational quantity. Okay? And we will use that quantity as a signature for our for non-classicality, for failure of non-contextuality. And you will see why we're using that quantity once we have the final result and we try to interpret it. But that quantity has to do with this property. Okay? The quantity, you can think of it as an average predictability, if you like. Okay? It's not the official name we use it, but yeah, I guess predictability. Or I like also calling it a source measurement correlation, like a correlation between a source that's preparing one ensemble of states and a measurement that's kind of receiving these states and doing things on these states. Okay? But whatever name you use for them, the idea is that this quantity is basically an average version of this predictability quantity. Okay? So I'll call it core. Just for source measurement correlation, and it's defined as pick one of these 9 hyperedges randomly, okay, with probability 1 over 9. So pick some I with probability 1 over 9, and then for each I equals 1 to 9, and then for each I with a 1/4 probability, well, okay, maybe this doesn't make such a nice reading. I will just kind of write it and then we see what it means. So for k equals 1 to 4, for each I there are 4 possible outcomes, right? Outcomes in this case, like in this, I mean these are like measurement outcomes, and I can think of these as like source outcomes if you're thinking of like a source which is spitting out these states, right? So that's the sense in which I'm using the word outcome here. You can use it in a more generalized sense than just measurement outcomes, right? So we look for the correlation between this measurement outcome, this measurement, when the preparation is ik. So ik happens to probability 1/4 for a given I, right? That's what this is. That's what I'm putting there. For a more general case, you can put a different distribution here, that's fine. But I'm just trying to keep the discussion simple right now. Okay? So what is this quantity doing? What this quantity is doing is, for each effect, it's asking if the associated source, which I label by the same label, like ik, how predictable does this source event, the source outcome, makes this measurement outcome? Right? That's what we're asking here. Right? And I'm averaging that for each of these measurement events. 1, 2, 3, 4. For measurement M, I'm averaging its predictability with respect to the associated source events. Right? And of course, like the thing is, in my operational theory, I'm completely free to choose these things as long as I'm satisfying these operational equivalence conditions. Okay? So in quantum theory, when this is a completely projective case, then we know that this quantity is trivially 1, right? It must be 1 because if I have a projective realization, like some 4 projectors here, which are a resolution of the identity, I take the corresponding eigenstates here for the preparations, and I just mix them uniformly, so I always get the maximum mix state, and so this condition is always satisfied for that choice of measurements and preparations. And of course, because I know that the quotient spectral theorem gives me a set of projectors which satisfy this condition, I know that I also satisfy these operational equivalences for measurements, right? So those 2 founding assumptions of the thing I'm going to derive are true for this setup, and so this quantity is 1, right? In quantum theory, right? It can be made 1 if you make these choices of measurements and preparations that I just mentioned. But we want to ask what's in a non-contextual morphological model, how high can you make this quantity? How predictable can you make all your measurements under the assumption that the ontological model is non-contextual. That's what you're asking. Okay? Okay, so the first thing, we introduce lambdas to begin talking about ontological models. So this is k equals 1 to 4. And now this p is in the operational theory, if you write it in terms of an ontological model, it becomes some mu pik lambda inside k given, I guess, mi lambda. Right? So right now I'm just written the ontological model. I've not imposed any non-contextual assumptions. Now, what we want. Okay, so now I'm going to put an upper bound on this. Again, not using any non-contextual assumption right now. So I want to take for each mi the most predictable effect, the effect which has the maximum probability for that given lambda. Okay, so I want to take the max of this over k. Okay, and that's what I'm going to do now. I just want something that's independent of k there. Okay, that's why I'm doing this. 4. So if I do a max over k, then I can take this thing out. This is like max over k. K I lambda. I mean, there's still a lambda here, so I'll put the lambda here. And then the remaining thing here is k equals 1 to 4 mu pik lambda. Is that okay? So I took the max of this and took it outside this k summation, but it's still within lambda. And this is just a piece with the k. And I actually want to move this 1/4 here from here to here. I mean, I guess you can see why I'm doing this, right? I'm doing this because I know that there is an operational equivalence here, which comes from, so these guys, this is 1/4 sigma k of mu pik lambda. Okay? This has a, sorry, I forgot to say, this has to do with the convexity thing we were talking about yesterday. It's the same convex mixture of the representations in the ontological model. Okay? So there is this. And once you have this, you can impose, you can use the assumption of preparation non-contextuality. I'm going to erase this. So now this is equal to, by preparation non-contextuality, so this is where the assumption comes into play, is equal to 1/9. Okay, I'll take the lambda out first, because I know that this is basically mu lambda, right? Like this is the thing independent of I. That's what I want to use. So it's some average with respect to mu lambda of this quantity, which is 1/9 I equals 1 to 9 of, I'll call this zeta, which is to do with the max probability of measurement mi. So zeta is this thing. Okay, so just write it here. Zeta mi of lambda is defined to be max over k of the effects of measurement mi, the response function for the effects. Okay, that's what theta is. So I've written this expression here. Right? Now, this is where the interesting stuff happens. Once you have this expression, I mean, I suppose it's kind of obvious now what's going to happen next. Is it? So I'm going to use convexity, right? Like I'm going to use the fact that this is an average quantity. Like it cannot be larger than the largest of these things maximized over lambda, right? So this thing is less than or equal to max over lambda of this 1 over 9 sigma I equals 1 to 9 of zeta mi. Is that okay? Yeah. I just take the largest value. These are all positive numbers, right? Okay. So I want to obtain a bound on this quantity by using this expression. Okay. And why would you expect? So I mean, of course, in order to have an arbitrary bound, it must be less than 1, right? Because quantum theory, we know, is contextual, like it achieves 1 or equals 1. So for this bound to be, I mean, the algebraic bound for this is 1. So for it to be a non-trivial inequality, it must bound something by less than 1, right? And why should we expect that it bounds with less than 1? The fact that it bounds with less than 1 is because this is an uncoverable hypergraph, right? The very act of proving the quotient spectral theorem, the non-existence of that map C, the 0, 1 value. So for example, imagine if the map C existed, if you could assign zeros and ones to everything. Then this quantity, zeta mi lambda, is going to be 1 for all I, right? Because there exists an assignment, so lambda is kind of doing these assignments. There exists an assignment which makes every measurement perfectly deterministic, right? Because it admits a deterministic assignment. So in the case where you can color these things, this quantity would be 1 for all mi. But when you cannot color them, when there is no map C, like when it's a logical contradiction, then you know that no matter what you do, you will end up having some probabilities inside because of like measurement on contextuality gives you this. One of the solutions was this one, right? Like this is a measurement on contextual assignment. So 0, 0, 0, 0, and you put a 1 here, 0's here, 0's here, and I can just put a 1 here, and that should finish the assignments. Maybe 1. No, sorry, this is a 0. And then, yeah, a 1 here. Yeah. So this is an example of a measurement on contextual assignment of probabilities. In this case, we see that this measurement, and this measurement, these three measurements, are the max probability is half, right? You cannot have any given that's more likely than half the time. The probability is not more than half for any given for these three measurements. For the other 6, there is a deterministic outcome. Like you can kind of maximize the probability to 1 for each of the other 6, right? I mean, you can confirm that, like because this one appears in 2. Each one appears in 2 measurements, right? So this one appears in 2 measurements, so 2 measurements can be made deterministic. And similarly for this one, 2 measurements can be made deterministic. This one and this one. And for the one here, this measurement and this measurement are deterministic. So there are 6 measurements which are deterministic, where zeta is 1. So basically what I'm saying is zeta mi. So there exists lambda such that when I say there exists lambda, I mean the lambda is going to assign probabilities to these things, right? Like, because these things are functions of lambda. So there exists lambda which assigns probabilities in a way that zeta mi lambda is equal to half for these measurements. 1 and what was the label for this? This is 6th measurement and this is the 7th measurement. For measurements 1, 6 and 7. Okay, and zeta mi lambda equals 1 for all I which are not in this but are in. So it's at 1 to 9, right? That's what I'm trying to say. Is that okay? I'm just reading this thing there, right? And now of course you need some additional. So first two things. Firstly, that the fact that this has to be strictly less than 1. For that, I didn't need to know the exact assignment I'm going to use here, right? Because the fact that it has to be strictly less than 1 is just because it cannot be that all the measurements are assigned 1s and 0s in this thing, right? Just because of that, because there's no deterministic assignment, so the max probabilities cannot be 1 for all the measurements. There has to be some indeterminism hiding somewhere. And this is an extreme example of like a crude measure of how much indeterminism you're going to need if you want to assume measurement non-contextuality is basically how many of these measurements can you make deterministic in an assignment of probabilities like this, right? So the claim is that if you look at the structure of solutions for this set of equations, then this one is one of the solutions that gives you the most number of deterministic measurements, gives you 6 deterministic ones. You cannot have 7 deterministic ones in any valid solution. Okay, those solutions don't exist. That's not a valid solution. If you try to make 7 measurements deterministic, you will not be able to normalize things the right way. Okay, so just by a vertex, you do an enumeration, like you write down that system of equations, and you just solve for the polytope that defines the set of probabilities, the set of assignments, and one of the extremal assignments, which cannot be understood as a mixture of others, is this one. And the reason I'm focusing on this one is because it's also the one that achieves the upper bound of this, right? Because it makes it as many deterministic as possible. So that means that this quantity, given this hypergraph, and now I'm already using measurement non-contextuality, right? Like the very fact that I'm bounding this thing is using measurement non-contextuality, because if I wasn't using measurement non-contextuality, I could make 2 copies of each of these things and things could be deterministic and stuff, and then there's no bound. So measurement non-contextuality is playing a role in providing that bound. Okay. So we're using measurement non-contextuality here. So now we have 1 and 9. So for this given lambda, which assigns those things, we can compute this quantity, right? Like, so this is it says for 6 of the measurements it's 1, the predictability, the max probability, and for 3 of them it's half, right? And so that means this is 15 by 18, so it's 5 over 6, right? Which is strictly less than 1. So this is a non-contextual model. So what are we saying? We're saying if you make the assumptions of preparation and measurement non-contextuality together with the operational equivalences I assume in order to justify those assumptions, then in such a theory, an operational theory which admits a non-contextual morphological model, this quantity is something you can observe in an experiment, is bounded by 5 over 6, right? Now, if you recall the ideal description of the quantum experiment, then you achieve 1 for this quantity, right? So quantumly you achieve, this is the quantum value, right? Like, core for quantum theory is 1. For non-contextual theories, it's 5 over 6. Theories is, you cannot do better than 5 over 6. Yeah? And so the gap between these two, it's important to know that there's a finite gap between these, right? Like, so between 5 by 6 and 1, this is the regime in which you can hope to witness contextuality using this inequality, as long as your measurements are sufficiently sharp, sufficiently precise, that you go just over 5 over 6, even if they're not perfectly projective. If they're perfectly projective, you'll achieve 1, right? But if you don't achieve 1, does it mean that you lost the contradiction? Because we saw that you'll lose the contradiction the moment you relax determinism, right? So if you don't assume 1, but you still reach 1, but you still go a bit over 5 over 6. So 5 over 6 is how much? Like, it's like 0.8 something, right? 83 something and 1. So as long as your predictability is above 0.83 or something, like 0.85 or whatever, you rule out a non-contextual model, right? That's the claim. So this is the sense in which this inequality is a noise robust version of the type of non-classicality that the quotient-spectral theorem hints at. Okay? The quotient-spectral theorem corresponds to the extreme limit of this where core equals 1. Okay? That's the regime in which you recover the insight from the quotient-spectral theorem. However, in a real experiment, you'll never have core equals 1. You'll have it slightly below. And if you were just thinking in terms terms of the assumptions in the quotient-spector theorem, that means there's no more quotient-spector theorem because there's no justification for like assuming determinism, no more determinism, no more sort of contradiction. But if you're assuming preparation and measurement of contextuality, you can still obtain a contradiction, and it's phrased in terms of the average predictability of your measurements, right? So if your measurements are completely noisy now, for example, if you go to the trivial POVM case, maybe just put like 1/4 identity on each of them or something, right? You're not going to suddenly violate that inequality, right? Like you will be any trivial POVM will not achieve 5/6 or whatever, right? Like it's going to give you like whatever 1/4. I don't know. Instead of everything is 1/4, it'll just give you something like that. So in some sense, the noise robustness is kind of hardwired into the inequality from the get-go because we're not assuming determinism. So we're not going to have those kind of absurd contradictions which come from distributed POVMs because we're allowing for all probabilities, right? Like I could achieve this with half identity, whatever, like, But so yeah, so I just wanted to. How much time do we have actually? Like I just wanted to make sure that you see the connection between.
35 minutes left.
45.
35.
35. Okay. Okay, so I will just briefly say something about how this example, this was the very first example of these kinds of inequalities. It's very generic actually, it's not special to this case. It's you can show that in you can generalize this simple example to arbitrary hypergraphs, which you cannot color, like uncolorable hypergraphs. It's the same principle, so it's not so surprising that it generalizes, right? So the reference for this one is this paper, 0208. And in this paper, it basically argues, so conceptually it uses the same tools that I discussed here. So conceptually there's nothing new in it. But what it shows is that the general form of these inequalities is always this, okay? Beta Q, where this beta is a hypergraph invariant that can be defined for any given hypergraph, invariant. When I say it's an invariant, it just means that it depends on the combinatorial structure of the hypergraph and not on how we label it and stuff, right? And I will write down the definition, then you'll see how it relates to the quantities that we're talking about, right? So this is just a generalization of stuff I just said. So if you take your chord to be, so gamma is your hypergraph. I'll label the edges of the hypergraph, which basically are hyperedges, these things, by E. And so if you index, if you go over the edges, which is what we're doing there, we're going over the 9 edges, and you use some distribution over the edges, so there we use a uniform distribution, but in general you can think of some other distribution. And for each edge, you look at both the source outcome and the measurement outcome. So I'm changing notation a bit here, but it's basically the k that I had earlier is like MESE, it could be k prime, and you want k prime equal to k, right? Like for this kind of correlation. And I sum this over MESE, probability of seeing MESE. So SE now are the preparations, like these are like the PIs earlier, and small SE is like the K. And so this is, I mean, maybe I'm not saying something very new here because it's basically the same quantity. Okay, the important thing is that this is this notation, like it's the same quantity, just slightly generalized. And maybe the important thing is that this quantity of beta is a generalization of this one, and it just says maximize. So So this is defined for arbitrary hypergraphs, not just the uncoverable ones, because it comes up in the other kinds of proofs, like statistical ones as well. Okay, so maximized over probabilistic models belonging to the general probabilistic stuff on gamma, and those which are indeterministic. I will explain what this means. And then take the sum over E, which are E are the edges of gamma, of the max predictabilities. So Q, E, zeta, M, E, P. I mean, lambda is like P here now, because P is kind of the probabilities that lambda assigns to the vertices, okay? So what is it saying? It's like I call it the weighted, because weighted by these QEs, max predictability. Okay, so it's like the weighted max predictability, which you maximize over. This is basically you can think of it as the measurement non-contextual and outcome indeterministic, and the ones which are not outcome deterministic assignments. Okay. Note that in this case, all possible solutions are outcome indeterministic, right? Like all of them are of this type, right? But in general, for example, for the statistical proof, there exist colorings which are deterministic, right? Like 1, 0, 0, 1, 0. 0, 0, and 1, right? So this is an example of a deterministic coloring here. But it also gives an indeterministic coloring, which is let's do half here, half here, half here, half here, and half here, and zeros in the middle. Then that's an indeterministic one, right? So this maximization will only go over the indeterministic ones. It will not go over the deterministic ones. That's what I'm trying to say. In a general hypergraph, you can have both kinds of assignments. In these ones, the logical proofs, you only have the indeterministic ones. So this definition is kind of important because it shows up when you try to do the same thing I did here for the statistical proofs of the quotient spectral theorem, the Priashko style proofs. And I don't think I really have time to do that part because this one already took a lot of time.
Maybe a question.
Yeah, I'll take questions maybe.
You've done this now and said that it's better than the kind of deterministic version of the Kogan spectrum because it's robust in some sense. But could you not imagine a kind of robust deterministic version where you say that, because I mean I imagine it's still not possible to assign probabilities to that graph where the probabilities are allowed to be, say, within 90 to 100%, 0 to 10%, right? So where you could say, okay, I'm allowing determinism up to a certain error rate, and then presumably you would get an inequality of the same style where you have some kind of margin of error.
Yeah. So I mean, mathematically, yes. I suppose. I mean, it sounds reasonable to me. If you just say that, okay, I don't ask for assignments between 0 or 1, but I in fact say 0 and 0.9 or something like that. I don't know. And so that's not strictly speaking outcome determinism because things can only be so deterministic but not perfectly deterministic. But then probabilities like I don't know if we're asking for probabilities to add up to 1 still.
Presumably, yes.
Yeah. So if you're asking, so the thing is that I think that the conceptual issue with doing that move is that this is a property that you're asking not of your operational theory. It's a property that you're asking of your ontological model. You're asking that in your ontological model, in reality, the world is such that things can only be made so predictable but not more predictable. Right? Like instead of just saying I'm agnostic, I mean they may be outcome deterministic, maybe they're not, but I allow for the possibility that they're outcome indeterministic. Instead of saying that, you're imposing a constraint. You're saying that oh, it's not perfectly outcome deterministic, but it's nearly outcome deterministic in this sense. So it's a new class of ontological models. It's a subclass of the kind that I'm looking at. So, and I don't know like how well motivated, like the only reason to think about these ontological models is because you kind of want to rescue the Contextuality theorem, is what I'm trying to say.
Yeah, well, I mean, the kind of, I would assume the motivation there would be the same in the sense that you say that, okay, if you want to rescue the Contextuality theorem, then you need your probabilities to be at least this far away from perfect.
Yeah.
Right. So if you can say that, then presumably you can say, okay, we can measure. So you can then do your test and say, okay, we find probabilities that are not far away from 0, 1. So therefore, that violates the or does not violate. Right? Could you not? I mean, I don't know if that's coherent with what you're saying.
So yeah, I mean that's what I'm worried about. Like if it is a coherent take, like because so here I was in my discussion throughout, I was kind of starting with the Contextuality theorem and then saying, okay, now we want to rescue this insight, and so we go to this general framework. But one of the things I wanted to do, which I didn't get to do today, it was in my plans, was I obviously only did the very first part I wanted to do. The other part was the statistical proofs, like the other kind. But then, so these are phrased within generalized contextuality, and then this, but then I wanted to actually really go to this example, which is an example of the failure of non-contextual ontological model, which is not inspired by quotient spectrum. So actually, like the framework itself, it's not sort of targeted toward the quotient spectrum theorem. It's more that the quotient spectrum theorem fits within this kind of general definition. But there are other types of contextuality in this framework, which would be the failure of this preparation and mentioned non-contextuality, but which cannot be seen as being coming from the quotient spectrum theorem. So, for example, you could use the quotient spectrum theorem to motivate this new class of ontological models which have these kinds of properties. But I'm not sure, for example, that the same the same strategy would work for these kinds of. I don't know. I'm just kind of confused about what the relationship of this set of ontological models would be to the set of ontological models we want. I mean, they will obviously be more restricted than the ones that we're looking at, right? Like they will impose some a priori by hand, like they want to impose some restriction on the determinisms in the theory, in the ontological model. Like it's just the by hand nature of it. Like it's just the fact that it's kind of a bit ad hoc to claim that it's only up to a certain degree. Mathematically, yes, like you can do that, but conceptually, is it interesting to rule out those things? Maybe it is, but I don't know. Is what I would say. Right? I'm not convinced at the moment that it is, but I could potentially be convinced as long as you can motivate it from operational constraints. Like somehow, like your assumptions about the ontology, the guiding principle is that you want to motivate them from what you see in an experiment. So that's some grounds for believing that it might actually be true these examples. Okay. So yeah.
I suppose the motivation would be something like, okay, we have measurement instruments and we can only measure up to say 90% accuracy or whatever. And so then we say, okay, that's our cutoff. If we want to have a result that discriminates between to know whether we measure. So if we measure something that's not 1, whether that is actually a violation or not a violation. So then you could look at discriminating, like allowing kind of 0.9 to still be counted as 1 versus 0.5.
Yeah.
Which would not be counted as 1.
Yeah, I mean, it could be some sort of possibilistic thing, I guess, like where you're. I mean, there is this, since you're mentioning this precision thing, or in some sense, like how well you can do things in the lab sort of situation. There's some, I'm not going to talk about it in these lectures, but there is maybe someday in another set of lectures. But there is this set of, there's another objection to the quotient spectrum theorem, which is different from the one that I've been talking about, which mine came from comparison with Bell and saying determinism is an assumption that you need to get rid of it. How do we do that? But there's actually a different set of criticisms which predates generalized contextuality. And if you want to look at it in the literature, it's quite interesting. And it's so these things are called finite precision nullification of the KS theorem. Okay. What this means, so when they use the word nullification, what they mean is it's not that the theorem is wrong. It's more that it's rather that in the real world where all your measurements are finite precision, like you're not going to do an infinitely precise measurement, you're never going to measure in exactly the direction you want to measure, but like it'll be somewhere around there. In that world, you can never test the quotient square theorem. And the key insight there is it's based on, okay, I don't even want to prove this, but it's based on a property of Hilbert spaces, which is the idea that for this map C that I was talking about, the 0, 1 value, the domain was the set of all projections, right? You can, if you restricted the domain instead of the set of all projections, to allow for some dense subset of the set of all projections, so which means you can approximate any projection to arbitrary accuracy by picking things from this within this dense subset, then actually such a map exists. So basically, what so this result is due to I think the original paper was due to David Meyer, and then later on Rob Clifton and Adrian Kent came up with more exhaustive models. So these are called Meyer-Clifton-Kent models, and these models basically exploit this property that there exists dense subsets where this map C can be defined, which can be colored. Okay. So which means that if you claim that you were doing a quotient factor experiment and that you observe this thing, right? For each of these, there is something infinitesimally close to it that I can pick where this equivalence breaks down, like the fact that this event is equivalent to this event in those two implementations. So basically, the whole hypergraph, which is what you need for a logical contradiction, kind of splits up, like all the edges separate because and they separate in a way that you're still pretty close to the actual realization which gives you the contradiction, right? But now you no longer have the contradiction even though you're epsilon close to it, as long as epsilon is greater than 0. Yeah. So any finite precision. So if you allow for if you think of finite precision experiments, you can never test the quotient factor theorem because of the mathematical fact that Hilbert spaces have this property that you can color, like you can find dense subsets which can be colored. If you restrict the domain to those dense subsets, those maps C will exist.
What do you mean by dense subset here? I mean, like a bigger set, right? Not a small set?
Smaller set which can approximate anything, any projection to arbitrary.
Right.
Like I mean, this limit point. I guess that's.
Any
I don't
set-
know. I'm not the expert on this stuff. Maybe Joseph can say something.
Oh, any sets such that you can find a sequence of vectors in your dense subset that converges to any vector in the Hilbert space.
Yeah,
Sure.
That's the limit point. Yeah. So in any case, so the idea is that for any finite precision you can find such a dense subset. So that's why it's kind of like, so that's a whole different set of objections, and then there you can say that because this finite precision is a bit like saying that you can only do things to this so well, and I mean it is still qualitatively different from this determinism thing, but I think so there are other approaches to kind of like handling this kind of so there was a long debate in the late 90s and early 2000s, so this is like the period of interest for this is like 1999 to 2004, 5, and 4 or 5 something, and I mean people argue that it uses so I mean okay, I'm not an expert on this whole debate, but if you just want to see an overview, there is a nice article by John Barrett and Adrian Kent from 2004, where they talk about, it's kind of a review of the debate that happened on about these models. And then, of course, like in 2008, there was this Kliashko group, right? This KCBS group, the statistical one that I was talking about. But even before that, people were talking about proofs, experiments on the quotient spectral theorems. There's a lot of literature, if you look at the literature, there's a lot of nature papers on experimental proofs of the quotient spectral theorem. And all of them kind of, I don't know, either they push it under the rug or they include some ad hoc things in their model to kind of try to account for this issue.
The Meyer-Clifton Kent's issue, you mean?
This is Meyer-Clifton Kent issue, yeah. And I mean, it's not been a big part of the discussion, I think, after this period. And the only other paper, the most recent one that I know, is by Andreas Winter from 2014. And this one says, you know, what does an experimental test of contextuality prove or disprove? Prove or disprove? And then basically kind of proposes some sort of restriction in the set of ontological models, which takes into account the finite precision loophole. So again, this is just like general knowledge about the field. Like if you're just interested in these conceptual issues having to do with the quotient spectral theorem. I mean, there's a version of this. There's an operation. I mean, I don't know if it's really an operational version of it, but there is something similar in spirit that happens in the operational case, and where we deal with it in a different way, because we're not assuming fluid spaces firstly. So the criticism doesn't directly apply, but what does happen is that, like, you know, you want these operational equivalences to be able to make a claim about non-contextuality. And the operational equivalences in general will not be exact. Like, you know, you did two different instances of the same effect. It's very rarely that you have exactly the same statistics. We're asking for exact equivalence. So you can criticize this proposal, everything I did, based on this idea that these operational equivalence is kind of a loophole, right? Like if things are never operationally equivalent, like if they're like a little bit different, then I don't have the justification for assuming non-contextuality, because, you know, it seems like I can distinguish them. So, but I have to distinguish statistical fluctuation from like what's really there. Like, okay, those are matters of detail. But one can get around a situation where you do not have exact equivalence without modifying the definition of non-contextuality, but using some additional structure in the theory, in the operational theory. And that structure, that at least in the very first version of these proposals, was to use the convexity of the theory. And that kind of resolves this loophole a bit. But in any case, I'm not going to talk about experiments and these laws, so I don't have to deal with these loopholes. And I just want to get the conceptual point across that there's a sense in which we have made the quotient spectral theorem noise robust, and the precise sense is this, like this gap in predictability. And yeah, in the limit we recover the quotient spectral insight where you have perfect predictability. But yeah, in between there's a finite gap, so you can have a noisy experiment and still witness contextuality. That's the key point, right? And yeah, so next time I will try to, maybe I won't spend as much time on it since I've introduced these concepts already, but I will try to give you a flavor for how to do this for hypergraphs which are colorable, which do not have this property that there's no solution. There are solutions, but still there are some statistical constraints. So you indirectly rule out the existence of the map C by observing some violations of some inequality, right? That's what we showed the last time for these statistical proofs, like that R quantity is less than or equal to 2, for example, for that pentagon example. So we will modify those inequalities next time. In order to, we will include these kinds of quantities, like we will add a figure of merit, which is basically going to be something like the average predictability of the measurements. And that's going to trade off against this R quantity there. And so basically, if your measurements are really bad, you can make your R very large, it's not a problem. But if the measurements are really good, then your R has to be limited in a non-contextual model. So, like in the limit where core equals 1, you will recover the R less than or equal to 2 inequality. But when core is slightly less than 1, the inequality is weaker, which means you need to work harder to violate it. So I will try to introduce that next time. And then maybe if I have some time, I will say something about this non-case inspired example. And I've never gone to GPTs, this was supposed to be about general probabilistic theories, but I think this is still, I didn't want to break the continuity from the last one, I just wanted to make sure that the central ideas get across. And so in the next one, I will maybe just do an overview of the GPT stuff. So I'll probably not go into a lot of details, but I will try to give you a sense of what all of this, so everything I've talked about is the connection between operation theories and ontological models. I will talk about how you reinterpret these results in the language of general probabilistic theories, like, which is kind of you obtain them from an operation theory by, again, quotienting away irrelevant details of the operation theory. But it's still kind of at the empirical level, it's not an ontological model directly. But, yeah. Okay, thank you.